Okay, now that we've talked about simple probability, or the probability of picking just one card, rolling the dice one time, we're now going to look at what we call compound probability. And with compound probability, we are going to look at choosing one item multiple times. So I may be rolling the dice two times, three times, or four times. I may flip a coin one time, two times, three times, but multiple times, not just once. So simple probability is once, and compound probability is multiple times. So there are two different types of compound probability, and the first one is called independent. And this is where the probability of the first pick does not affect the probability of the remaining picks. It is also known as, for the most part, as a replacement problem. That means I'm going to pick something and I'm going to put it back in the thing and allow it to get picked again. And so that is really just the probability of event A times the probability of event B. Now we also have what we call dependent probability. This is the probability where the first pick does affect the probability of the remaining picks. Usually we see this as a non-replacement problem. So I may pick something and then I leave it out, which affects the probability for the rest of the picks, because now I have one less number on the bottom. So if I pick an ace card, I now only have 3 aces out of 51 cards left in my deck of cards. So those numbers have now changed because keeping that ace out of the deck has affected my total numbers. And so now that means that we could do the probability for normal on the first one, but on the second one, we now have a little bit of a change. And how does that change affect us? Usually we have one less possibility, unless it's a repeater. So the probability of 2 aces would mean that I have 4 out of 52 cards for my first ace that I pick. But if I keep an ace out, now I only have 3 aces out of 51 total cards. So both numbers changed because I was picking the same thing. But if I have the probability of an ace and then a 3, then I would have 4 out of 52 aces times, now that I keep an ace out, I still have 4 3s in the deck, but only 51 total cards. So when we have a repeater, the top number changes also. And so this is that whole idea of dependence. That second fraction is going to change in a certain way depending on what you're picking. So, a sample problem. Sarah goes to the school store to buy a pencil. The school store has 12 blue pencils, 8 red pencils, and 10 green pencils. So altogether it looks like there's 30 pencils. The pencils are all in a can mixed up. What is the probability that Sarah randomly picks a red pencil, puts it back, and then picks a green pencil? Since she puts it back, this is an independent case, so it's always going to be 30 pencils that she's picking from. So her first choice for a red pencil would be, well, there are 8 red pencils out of 30 pencils. And then my second choice would be a green pencil. Since she puts it back, I still have 30 pencils to choose from, and there are 10 green pencils. So that means this is an 80 out of 30 times 30 is 9 with 2 zeros. And that's our probability. Now we're not going to work on reducing this fraction, mainly because we've had such problems with people not reducing completely that we don't want to have to deal with that. We want to make sure your process is correct for the section. So next problem, what is the probability Sarah randomly picks a red pencil, buys it, and then picks a green pencil? So the red pencil on the first pick is still 8 out of 30. Now that she buys the pencil, it doesn't go back in. Now we only have 29 pencils to choose from. Now of those 29 pencils, 10 of them are still green. So now this is an 80 out of, well, I've got to multiply that. 870. So it's actually a better probability, a better chance of that happening. Okay, for our next one, what is the probability Sarah picks and buys a green pencil, then John picks and buys a blue pencil, and then Josh picks and buys a red pencil? So let's see, a green pencil, we've got 10 out of 30 pencils. Now she keeps it because she's buying it. Normally you don't buy it and then put it back. You buy it and you keep your pencil. So now John's going to pick a blue pencil, so now there's only 29. Blue pencils, there are 12. And then Josh is going to come pick a red pencil, so now we're down to 28 pencils, and 8 of those are red. And so now we would go ahead and multiply those, which gives us 960 over 30 times 29 times 28, 24,360. And then for our very last problem, what is the probability Sarah picks and buys a green pencil, John picks and buys a green pencil, and then Josh picks and buys a green pencil? So there are 10 green pencils out of 30. Then she picks a green pencil and keeps it. So now we've got 29 pencils. And how many of them are green? Well, since she kept a green one, now we only have 9 green pencils. So now when it comes time, wait, that was John, so now we're up to Josh. So Josh, now there's only 28 pencils and only 8 of them are green. So now we have 10 times 9 times 8 over, so that's 720. And what's nice is that bottom number is still 24,360. And we can leave our numbers like that just in case. Now if we wanted to turn these into percentages, we could go ahead and do 720 divided by 24,360, and it would give us that proportion. Which we can then turn into a percent. There's a 2.96% chance. That's with rounding. So approximately that percent chance of that happening. And we can go back up and do the same thing. So that way we're practicing with our proportions. So 960 divided by 24,360 gives me about a 3.94% chance. And then up here, 80 divided by 870 gives me a 9.2% chance. And so that's always an option to you, but you cannot skip the original fraction. You must still have this original fraction, but if you want to also turn it into a percent, that is up to you. And the reason why is most people can make sense of those percents better than the fractions. The fractions don't mean a lot to them, but the percents do.